Hello and welcome. My name is Ashish Ahuja. I'm an applications engineer with Texas Instruments, and I'm really excited to introduce you to the brand new Tiva C-Series TM4C129X family of ARM Cortex M4 microcontrollers for applications that connect, communicate, and control. In this video, we will take a look at the LCD controller module on the TM4C129X devices. But before we do that, I want to talk to you about the TM4C129X devices that they're built on the TI proprietary 65nm technology. High integration and smaller feature size results in a smaller die, hence smaller package footprint, resulting in reduced cost and increased board savings on your application. Profilic connectivity options such as integrated Ethernet MAC and PHY, USB on-the-go host device, CAN, I2Cs, SPIs, and so on allows for connectivity, communication, and control over a wide variety of interfaces. The seamless integration of these features, along with sophisticated analog peripherals and a floating point unit, provides a scalable and cost-effective solution to a large number of home and industrial automation and control applications. So, by the end of this video, you will be familiar with the LCD controller module and its different modes of operation on the TM4C129X devices. We will also briefly discuss about how to set up and initialize the LCD controller using the APIs in the driver library and graphics library that are provided in the TivaWare for C-Series. So let us take a look at a very basic system with the LCD controller, a microcontroller, and a LCD screen. In such a system, the raw image data is stored in a buffer in the SRAM. The LCD controller reads the data from the image buffer, translates it into a format that LCD screen can display, and sends it to the LCD screen with correct signal timings such that the desired image is displayed correctly. The end goal in such a system is to display the image on the external LCD screen. A configuration like the one shown on the screen only works for some applications because it has several limitations. Firstly, the CPU core must read every pixel from the SRAM and rewrite it to the LCD controller. This consumes a significant amount of processor's bandwidth. Secondly, the SRAM may not be large enough to hold all the image data that you need. So to solve this problem, TI has developed a new integrated LCD controller in the TM4C129X microcontrollers, which has a large frame buffer to store large images and can be operated in different modes that we will discuss shortly. The LCD controller on the TM4C129X devices provides a configurable parallel interface to connect a wide number of displays with the purpose to make it easier for the microcontroller to move image data from the display buffer to an LCD screen while getting timings and formatting correct. Some key benefits of using the LCD controller are that the target LCD screen can be constantly refreshed through a dedicated DMA engine, and the index colors can be converted to the correct format for RGB output without processor's intervention. As shown on the screen, the LCD controller module is integrated in the TM4C129X devices, and it has been designed to ease the load on the CPU. The implementation requires CPU to only write in the SRAM buffer when the image to be displayed changes. The LCD DMA engine will continuously read the image data until the CPU requests it to stop. Since the LCD controller has its own dedicated high-priority DMA engine, it doesn't have to steal cycles from the micro DMA module in the system. The LCD DMA engine has a small FIFO, and it allows periodic interruptions as necessary. In systems with very limited SRAM, the raw image data can be saved in an external memory, such as SDRAM, which can be connected to the microcontroller over extended peripheral bus, also called EPI. This configuration is shown on the screen. You will be required to configure several parameters such as the image data formats in the memory and signal requirements for the particular LCD screen that you are using. These parameters, along with and several others, can be provided through configuration registers in the LCD controller, and they are supported through TivaWare APIs and structures to make the configuration process a lot easier. Interestingly, the LCD controller has been designed to operate in two modes: Raster Mode and LCD Interface Display Driver Mode, also known as the LID mode. Each mode is specialized for a certain set of inputs and outputs and can be configured to fit the timings and protocols of a wide variety of displays. Raster mode is for taking raw image data such as RGB, grayscale, indexed, etc. from the memory and send it to the controller-less display without processor's intervention. It provides a mechanism to constantly refresh the displays with the image data and supports up to 24-bit color. On the other hand, the lid mode is for sending serial image data or otherwise to an external display device. In this mode, the CPU intervention is allowed, and in the next section of this video, I will explain each of these modes in more detail. In the raster mode, the image buffers can reside in microcontroller's internal SRAM or in the external memory connected via EPI. The image buffer contains a space for the color palette data and image data. LCD DMA Engine copies color palette data to the LCD module's internal color palette SRAM. LCD DMA Engine would send image data to the main LCD controller image data FIFO. The LCD DMA Engine and the raster controller will continuously retrieve more image data from the SRAM frame buffer and use it to refresh the display continuously. The image data path is active constantly once the raster mode has been configured and enabled. This means that the display will be continuously refreshed with the data from the frame buffer. The CPU can still write to the frame buffer while this is happening, and the display will be updated with the new image on the next refresh. Both DMA only and ping pong modes are allowed so that the images can be dynamically updated. The output of the raster block is tailored to controller-less LCD screens and consists of standard RGB data lines and control signals. Since the control and data signals are intended to go directly out to the LCD screen, the raster mode control supports several options for adjusting the timings of these signals, including polarity, number of pixels per row column, H-sync, V-sync width, delays at the beginning and end of line transmission, delays at the beginning and end of frame transmission, AC bias fin frequency, etc. Because of all these features, the LCD controller on TM4C129X devices can be used to drive most active and passive display types. Alright, now let's take a look at the LCD interface display driver mode, the lid mode, which is based on the concepts that we had briefly discussed earlier in this video. The image data still probably resides in SRAM, and the LCD screen now reads commands and datas, not RGB signals or H-sync and V-sync signals. In the lid mode, the LCD controller is pretty much replacing SPI, I2C, or some other serial peripheral. Depending on the display, the MCU may need to read data back from the LCD screen, so each exchange of data is bidirectional. The LCD DMA engine can still be used to load commands and data into SRAM buffer. You will need to configure the LCD DMA engine to read the commands which will be sent to the display. In order to be able to replace several different protocols, lid mode provides a basic interface and a series of registers to configure the output. The basic block diagram is shown on the screen. 4 main registers are exposed to the CPU for reading and writing. Lid mode supports different configurations. Exactly which signals are provided depends on the configuration being used. Some are synchronous while others are asynchronous. As in the raster mode, the output signals have variable timing parameters. One can change the output signal polarity, setup, hold, and the duration of read and write strobes and delay between the write commands. Now, I want to briefly spend a moment and talk to you about how you can configure and initialize the LCD controller and create compelling GUIs for your applications involving TM4C129X products. We have developed Tiva for C series. It is a suite of royalty-free pre-compiled libraries and source code for the drivers and examples to use with TM4C129X microcontrollers. The peripheral driver library provides an API function call based convenient interface to initialize and configure LCD controller, direct access to lid controller, and LCD DMA engine. The drivers LCD.C and LCD.H are located in the Tiva for C series. Extensive documentation that includes information about function prototype, return type, arguments, etc. is also available in Tiva for C series. We have also developed graphics library that provides a set of graphic primitives and widget set for creating GUIs. It is based on 3 layers: display driver layer, graphic primitives layer, and widget layer. The source code along with extensive documentation are provided in the Tiva for C series for your reference. Images on the following screen shows examples of graphics created using our graphics library. By the way, the graphics library is written in C and comes with several utilities that allows you to render your own fonts, create graphic elements such as checkboxes, push buttons, radio buttons, sliders, list boxes, etc. So today, we briefly looked at the LCD controller module and its different modes of operation on the TM4C129X family of microcontrollers. Specifically, we discussed the raster mode and lid mode in detail. We also talked about how to set up and initialize the LCD controller using APIs in the driver library and graphics library that are provided in the TivaWare for C series. Equipped with this knowledge, you are now ready to create your first project using LCD controller. I encourage you to review the product datasheet and visit the link shown on the next screen should you need more information and support. We will be back with more innovative products. Till then, ciao.